Hello everyone! The central theme of this series is that fossils tell you so much more than simply that something died. Today, we're going to look at a field of study based entirely on what fossils and rocks tell us about the ancient climate. So, let's jump right in. Paleoclimatology is the study of ancient climates, and this field shows that the Earth's climate has varied greatly in the past. These changes were always the result of completely naturalistic phenomena, from volcanoes to ice age cycles to shifts in the amount of atmospheric carbon dioxide, and more. And nowhere in the rocks or fossils is there any evidence that the Earth is only 6,000 years old or that a global flood occurred. So let's look at a few examples. Admittedly, the first place we're going to go concerns neither fossils nor rocks. Ice cores. Researchers can drill into the ice and produce ice cores that contain a number of different indicators of the ancient climate. For one thing, they can tell us how the ancient atmosphere's composition has changed over time. Ice cores can also tell us about oxygen isotope ratios. Atmospheric levels of oxygen-18 correlate to ocean temperatures. As the ocean warms, more oxygen-18 is evaporated. Sometimes ice cores have pollen in them, and pollen can tell us a lot about the environment. In fact, they can tell us so much that they'll be getting their own future video. Tree rings are another method used to understand the ancient climate, a field called dendroclimatology. The size of tree rings can inform us about the annual amount of precipitation and average temperature in an area. Then, this can be cross-checked with other trees in the area to give us an accurate picture of the local environment. Similarly, corals can be utilized to understand the average ocean temperature in an area. Remember the diatoms and foraminifera that we met in index fossils? They can be used to infer past climates. Part of the reason is that they make calcium carbonate shells, which record much about the ancient Earth. For example, diatom biodiversity is negatively correlated with higher ocean temperatures. Also, the morphology of diatoms can be affected by temperature, as seen in Thalassiocera pseudonana. And concentrations of isotopes of lithium in foraminifera shells indicate continental weathering. You see, carbon dioxide is consumed from the atmosphere during continental weathering, while positively charged ions, such as lithium ions, are transported to the ocean. Those ions, depending on the type, can then end up being incorporated into the calcium carbonate shells, which then inform us about the weathering. And even which polymorph of calcium carbonate was used to make the shell, whether calcite or aragonite, can inform us about the past. For example, geologists have figured out that the oceanic precipitation of aragonite corresponds to climatic greenhouse periods, while the precipitation of calcite corresponds to icehouse periods. But also, slower seafloor spreading causes higher precipitation of aragonite, while faster seafloor spreading causes higher precipitation of calcite. Animal and plant fossils can be used similarly. Clearly, animals and plants without adaptations to very cold climates won't be found in cold climates. For instance, if you go to the American Southwest, specifically to the Triassic Chinle Formation, then you'll find the remains of an area that was once a large wetland. You'll find numerous coniferous trees, which is why an area of the formation is named the Petrified Forest National Park, and the palm-like San Miguelia. You'll find Hybodont sharks, coelacanths, amphibious metaposaurs, and the strange aquatic archosaur Vanclevia. You'll find phytosaurs like Postosuchus, adasaurs like Typothorax, Rauisuchians like Postosuchus, the diapsid Trilophosaurus, and the dicynodont Placerius. And you'll find dinosaurs like Chindosaurus, Tawa, and Coelophysis. Taken together, these organisms depict an environment of rivers and lakes, of dense woods, not a cold climate or the desert that it now is. Aiding paleoclimatology is histology, the study of plant and animal tissues under a microscope. Histological analyses of the Permian temnospondyl apatian have been especially interesting as recorded by the 2010 paper Paleoecological and Paleoenvironmental Influences Revealed by Long Bone Paleohistology, the example of the Permian branchiosaurid apatian. Lines of arrested growth, or lags, clearly represent arrested growth of the bone, which can be for various reasons, but a common one is hibernation, since the growth of bones slows down during hibernation. What's interesting about this paper is that the fossils that are inferred to come from relatively high altitude lakes have double lags, 2 per year, as opposed to the normal pattern of 1 lag representing a year in low-lying lakes. The reason for the single period of hibernation in the low-lying area is simply the lake freezing up over winter. But there are 2 lags in the high-altitude lake fossils because there was pronounced seasonality, such that apatian hibernated in the winter when the lake froze, but also underwent estivation, or periods of prolonged dormancy, during the summer when the lake dried up and conditions became more arid. This same pattern has been observed in newts today, which is why we know what it means in apatian. And last but not least, rocks can inform us about past climates. For example, we know what the early Earth's atmosphere composition was because of geochemistry. We know that the Earth's early atmosphere was primarily composed of nitrogen, carbon dioxide, and inert gases. Later, banded iron formations and evaporites tell us that there was a great influx of oxygen into the atmosphere, which we understand now was caused primarily by cyanobacteria. Rocks have always been silent witnesses to the Earth's changes, so when creationists ask, "Were you there?" we should reply that the rocks were. We can also see that the Earth heated up significantly during the Permian-Triassic extinction, as well as the numerous global climatic fluctuations that occurred throughout the Paleozoic, Mesozoic, and Cenozoic. Another extreme example of such fluctuation is something called the Paleocene-Eocene Thermal Maximum, or PETM. Around 55 million years ago, lasting for about 200,000 years, it was the hottest time period since the age of the non-avian dinosaurs. With global average being 8 degrees Celsius warmer than today, permanent ice was virtually non-existent. Scientists know this from various different lines of evidence that were previously mentioned. Oxygen-18 isotopes from foraminiferous shells show a spike in global average temperatures during this time, and fossils of tropical plants have been found at high latitudes, sometimes even beyond the Arctic Circle. Such an ice-free hothouse would have been perfect for cold-blooded reptiles, and indeed, as the fossils show, they were thriving as the largest land animals. This is when the giant, smart car-sized turtle, Carbonemys, and the massive titanoboa roamed the land. It was a time when the largest animals that are known to us were snakes. For more on the PETM, I recommend the YouTube video called The Last Time the Globe Warmed by PBS Eons. Please check it out. Thus, combining studies of rocks, fossils, tree rings, and ice cores can tell us a whole lot about the ancient climate and the ancient world. So, thanks for watching, and I'll see you next time.